Hello everybody. I would like to welcome you to the deep dive presentation of the OPC UA for machinery. My name is Timo Helfrich. I work for the VDMA here in Frankfurt, and my job here is to support our working groups and every aspects of information modeling. I'm also part of the harmonization working group OPC UA for machinery, and I organize several cross-industry topics regarding OPC UA in the VDMA. Today I would like to give you a deeper, more technical insight into OPC UA for machinery. I would like to show you the development process and the resulting information models. At the beginning, I would like to give you a short overview of our working group and show you the motivation of the working group. As you already know from other presentations, the VDMA is working on OPC UA companion specifications in different industries, and therefore we have various industry-specific working groups. From the experience of our advancing OPC UA working groups, we noticed that some information keep coming up across the industries. But most of the times, these models differ in the way they are modeled. The VDMA wants to ensure interoperability, so we say that these standards need to be harmonized, and therefore we want to create a common handwriting for OPC UA companion specifications. So we founded the working group OPC UA for machinery. The goal is to develop companion specifications for all machines and components of discrete manufacturing. We want to describe basic building blocks, which can be taken up in various companion specifications or by vendors in their own information models. But we focus mainly on the mechanical engineering. Sometimes it fits for other sectors as well. These building blocks, which we model, can and should be used by our working groups and the published and coming companion specifications. They can also extend our models. So the OPC UA for machinery is the basis for the development of new companion specifications. As we define information models for content which comes up across the industries, we reduce the development times in future working groups because they don't have to handle it again. The OPC UA for machinery is the base specification for the mechanical engineering industry. So for example, when we take a look at the companion specification for machine tools, this is already based on machinery. The machine tools specification build even more specific models with it. They build models for lasers and something similar, and all those are in the end based on machinery. To show you the dynamics of our harmonization activity, I would give you a short insight into the short history of the OPC UA for machinery working group. The group was established in September 2019. After a short ramp-up phase, where the most important topics for harmonization were identified, we already started working on the first companion specification in October 2019. The most important topic which we identified was machine identification, so therefore we started with machine identification. In April 2020, the first companion specification was released as a release candidate and was available for the public for comments. At the same time, the group started working on the next topics on our roadmap. These were component identification and machine states. We organized to have two groups working at the same time, so we have a faster development process here. In September 2020, the first specification machine identification could be published. And last month we put out the next release candidate on component identification, which is now out for comments. Now I want to get into detail on the first release. This handles machine identification. This is the first fully published specification of OPC UA for machinery. It is available on our website opcua.vdma.org and is totally free of charge for download. It describes two use cases. The first one is machine identification and nameplate, and the second one is finding all machines in a server. I will go into more detail on that later. The OPC UA for machinery is not only published as a VDMA standard sheet, but is also an official OPC UA companion specification which is published by the OPC Foundation. Both documents are totally identical, except for the title page which you see here. But now let's have a look into the specification. If you open the specification, you will see the scope on the first pages. For many working groups, this is quite easy to define because they know their industry very well and they know the system boundaries of their machines. But for the machinery group, this was kind of a challenge because we wanted to make it possible for all machine manufacturers within the VDMA and even the whole mechanical engineering industry to use our specification. So you see a scope which is a quite broad definition of a machine. It fits for a wide range of applications. According to our scope, a machine is any piece of equipment that converts energy into mechanical movement, heat, or something similar to perform a task in an industrial context. This definition is followed by some examples, which demonstrates again the versatility of the scope of this specification. So for example, a machine could be a common machine or a machine to common understanding of machines, like for example machine tools, but the machinery is also applicable to robots, ovens, or machine vision equipment, for example. An important principle of the OPC UA for machinery is that we define building blocks. These are modular building blocks that can be added to any other specification or information models in general. Maybe we should start with some basic information on OPC UA information modeling. OPC UA information modeling is based on object-oriented programming. There are types which can be compared to classes, and classes as well as types serve as blueprints for the description of real objects. Types contain properties, parameters, and functions that describe a real object. In object-oriented programming, we sometimes have classes that are built by composing other classes. This is called multiple inheritance. But in OPC UA, this is not possible without further ado. So to make it possible, so-called add-ins are used. For example, we have the building block 1 type on the right. This could be a feature which you use in several of your machines, and you want to use this feature multiple times. On the left side you see the specific machine type. This is the definition of a specific machine which can be instantiated. If you want to use the feature of building block 1 in your specific machine, you can reference it easily by using the has add-in reference. So this is the basic principle of add-ins. This is really important for our OPC UA machinery because it allows companion specifications to easily retrofit the contents of machinery. Therefore, we have no breaking changes in the companion specifications. Breaking changes are changes that invalidate a previous version. So for example, a breaking change occurs when a parameter that was mandatory before, so mandatory in an older version, is now defined as optional in a newer version. So a client that knows the older version expects this parameter, but this parameter is now no longer necessarily present in a server that implements the new version. So the old client can't expect the new parameter. So let us come to the use cases included in the first specification. The first use case is machine identification and nameplate. Our goal was to enable the user to identify a machine uniquely, and this across all servers. Also, we wanted to provide standardized information about the machine, like serial number or manufacturer, and we want to provide user-specific information like the name of a machine in a factory context. OPC UA experts among you already know that OPC UA for devices already provides a model for identification. The machinery working group took a look at it, but has found that that was not sufficient to identify a machine uniquely. Nevertheless, we identified and reused parameters from the eye. This achieves higher interoperability because we are using common models. So we use the eye vendor nameplate type and the eye tag nameplate type for our model. The eye at the beginning of these types stands for interface, which is a similar approach to add-ins. It also allows the multiple use of the same parameters. The eye vendor nameplate type provides information provided by the manufacturer. This is the product instance URI, so a URI that should be unique for each machine worldwide. The manufacturer URI, an URI that allows identifying the manufacturer. The product code, which gives the entry possibility for example, article numbers. And we have hardware and software revision, which gives information about the version of a machine. Then we have the device class parameter that classifies the machine type of the machine. And we have model, manufacturer, and serial number, which are self-explanatory. As well, we have the iTag nameplate type. This contains parameters that are filled in by the customer. You see here the parameters asset ID, which name an ID as it could be found in catalogs, and the component name, which is more of a colloquial name of the machine. From this, we developed two new interfaces, which are called iMachine vendor nameplate type and iTag nameplate type. Both derive from the DI interfaces, which we see before. The iMachine vendor nameplate type adds year and month of construction parameters. These give information when the machine was built. A day of construction is not provided by all manufacturers, which was part of our discussion in the working group. Therefore, we said that a day of construction is not needed, but other companion specifications and other working groups can extend our model and add it if they see it feasible for their use cases. The iMachine vendor nameplate type also adds the initial operation date, which provides the exact time at which the machine was first switched on. The iMachine tag nameplate type on the right side adds the parameter location. It's a simple option to provide the location of a machine, for example in a factory context. But this is just a simple string, so it should not be used to provide GPS data or something similar. The iMachine vendor nameplate type ensures that a machine can be uniquely identified. Therefore, the parameters product instance URI, the manufacturer, and the serial number are mandatory. For a more detailed explanation, you can take a look into the specification. There's also described under which conditions each parameter is recommended to use. The machine identification type is the object type for identification. It is formed by using the two interfaces we defined before. So in the end, this is the add-in which can be added to any type with the has add-in reference. There's a parameter, which you can see below, that is called default instance browse name. So if the machine identification type gets instantiated, for example it gets applied to a real machine, then this object has to be called identification. As this is maybe hard to understand, I have an example for easy understanding. On the left side you see the example machine type that could be defined in a companion specification, for example. This contains information about the machine, and it also adds the machine identification type with the has add-in reference. But as you see, this already creates an instance of the type, so we see the object identification or two double point identification here. If this now gets instantiated for a real existing machine, an instance of the example machine type is created. This contains the identification object according to the type definition on the left side. The parameters can now be filled with real values, like you see here in quotation marks. So just to make sure, on the left side, the to identification is exactly what we describe in the machine identification type, just an instance of it. Now we come to the second use case, which is finding all machines in a server. This should allow the user to easily find all machines managed by one server. This is of particular interest when aggregating several machines into one server. For this purpose, we defined a machines folder. This is like a folder in Windows where you organize all your machines. All machines that contain the identification add-in are referenced via a organizers reference. There's no specific machine type prescribed, so you can use whatever type you want. Therefore, existing companion specifications can reference their existing machine types. So it can be an example machine type, like you see here, but it can also be a motion device system, from the robotics spec or anything else. A special feature from the machines folder is that it is referenced directly by the objects folder. And the objects folder is the entry point of every OPC UA server. So you have a list of all machines, and this can be found with a few OPC UA service calls. To complete the specification, we define conformance units. Conformance units are testable units of functionalities that an OPC UA server or client can provide. The first specification describes 3 conformance units. The first one is machinery identification, which ensures that readable access to the parameters is possible. The second one extends the first one, that writable access for writable parameters is possible. This concerns all values that are filled in by the customer. So a server has to provide these writable values. Otherwise, it would not make sense to have writable parameters if you can't write into values. The third conformance unit ensures that the machines folder is available and references the machines correctly. You can group conformance units into profiles. These allow certification of OPC UA solutions. We defined profiles in the companion specification as well, so that a manufacturer later on can advertise that the product fulfills certain functionality, or a customer can ensure that functionalities are available and correctly implemented. After I presented the first specification, which is released now with machine identification, I want to give you a short insight into the results of the component identification. The results of component identification are published in a revision of part 1. So it adds to the machine identification 2 use cases: component identification and nameplate, and finding all components in a machine. The first use case was component identification and nameplate. Our objective here was to allow the user to identify the component of a machine. But this does not have to be necessarily uniquely. At the same time, we wanted to provide the user standardized information about the component. To this end, we examined the results of the machine identification. We evaluated to what extent they are applicable to components. From this, we developed the machinery component identification type that you see here. As a result, the location parameter has been removed. This has been removed because the location is given by the machine which the component belongs to. Secondly, the device revision has been reintroduced. This was not relevant for machines in our opinion, so we didn't define it in machine identification. But we found it relevant for components. The device revision describes the overall revision level of a component. It increases when either the software or hardware revision of the component increase. Since no globally unique identification is required anymore, the product instance URI is no longer mandatory. Only the manufacturer URI and the serial number stay mandatory, as you see here. The product instance URI is now optional. There's a special feature in this information model which could be of interest to other information modelers and editors of companion specifications. As you see, the machine identification and component identification are quite similar. The component identification, however, has looser modeling rules. The machine identification has one more mandatory parameter. So we considered in the group to define the machine identification type as a child of the component identification. This would not have been a breaking change to the machine identification spec, but it does not really make sense semantically. Therefore, we found a solution that we created an abstract supertype. This abstract supertype covers the common parameters from both identification types. So machine identification and component identification inherit from this new type. The new type is called machinery item identification type. Since it's abstract, it cannot be instantiated. So irritations and misuse should be avoided by design. The far more interesting use case in the second version is finding all components in a machine. where a user wants to have all components of a machine listed. For this purpose, we developed the machine components type. This is also an add-in that can be attached to any machine type, like you see here for the example machine 1. The machine components type lists all components of a machine when it's instantiated. The object references all components via the hasComponent reference, and all the referenced components should contain the identification object. However, it does not matter whether it's the machine identification or component identification. Accordingly, a machine can also be a component of another machine. Except for additional conformance units and profiles, these are the contents of the second version of OPC UA for machinery. So now that we have completed the identification topics, the next topics are machine states, job and dataset management, and process values. But there are far more topics on the roadmap. As already seen on the timeline before, machine states is already being dealt with in the group. The topic process values, which is shown separate here in the diagram, is not directly handled by the machinery working group. There's another group which wants to better the engineering unit system in OPC UA. As the machinery working group, we think that this is preliminary work for the process value topic, and therefore this is currently on hold. But all in all, I think we can all expect further publications of the machinery in near future. Let me just briefly summarize. The OPC UA for machinery is the harmonization activity for the entire mechanical and plant engineering sector. The harmonized standards provide higher interoperability between machines. The working group OPC UA for machinery defines building blocks that can be easily integrated into companion specifications. The building blocks for machine and component identification are currently available. Just a short reminder, the first machinery companion specification, the new release candidate, and many more companion specifications are available for download on our website opcua.vdma.org. There you will also find further information and news in the OPC UA environment of the VDMA. And a second note, if you are a member of the VDMA or the OPC Foundation, I can also recommend you to participate in our joint working group on OPC UA for machinery. If you want to take part in it, please contact me or my colleague, Mr. Heiko Herden. For now, I can only thank you for your attention, and I am at your disposal for any further questions.